Okay, so I think we are online and now we can start with the lecture. So, welcome to lecture 19 of this course on solid mechanics. And today we will be continuing from where we left in our last lecture. So, if you remember, in the last lecture, that was lecture 18, we talked about plane stress condition, and today we'll be talking about something which is known as plane strain condition. So from stress to strain. So let me share the screen and then we can start with the lecture actually. So I think my screen is visible to everyone. So we can actually start. So what we will be talking about today is what is known as plane strain condition. So suppose there is a given state of strain, and for that given state of strain, there exists a coordinate system E1, E2, E3 such that epsilon zz, gamma yz, and gamma xz, all these three conditions are equal to 0. And if this condition is satisfied, we say that the body is under the plane strain condition. So, so if we come here and we are talking about plane strain, so how will the strain tensor look like? Well, if I write it in matrix form, the strain tensor will look something like epsilon xx gamma, I mean gamma xy by 2, then here it is gamma xy by 2 epsilon yy, and all the remaining components are actually 0. And if this condition is satisfied, we say that the body is under the plane strain condition. So as you remember, for plane stress, we have a sigma, which was of this form. And for plane strain, we start with the strain or epsilon, which is of this form. So the concept is kind of similar, but instead of using it for stresses, we are now using it for strain. So this is how it looks for the plane stress condition. So this is plane stress, and this is plane strain. Now, for plane stress condition, we talked about that plane strain condition can be visible or can be observed if the dimension of, I mean, one of the dimension of a plate is significantly smaller as compared to the other dimensions. So if you remember, we drew this plate and then we said this side is A, this side is B, and we have this height which is C. So this height is C, and plane strain condition holds if C is much less than A and C is much less than B. Now this is not the only condition. Obviously, plane stress condition also depends on the force and the boundary condition, but this is one of the condition that we discussed in our last lecture. So now the question is, when can we find plane strain condition. So when can we find plane strain condition? So that is the question. So plane strain condition is observed is one of the dimension is significantly larger than the other two dimensions. So previously it was significantly smaller, and now we are saying that it is significantly larger. So so suppose you have a thin cylinder, and in this case this diameter d, and let us say this is my length L. So if d is much more small than L, or I can say L is much greater than d, then you can find plane strain condition. Obviously, it will again depend on the loading condition. Similarly, if you have a plate, I mean, that will no longer be a plate, that will now become a square beam. So you see one of the dimension is now significantly large as compared to the other two dimensions. So now this is my C, and then A and B, then C is much greater than A, and C is much greater than B, and this becomes the case for obtaining plane strain condition. But again, a word of caution, only having one dimension significantly smaller will not give you a plane stress condition. It also depends on the boundary condition and the loading condition. Similarly, only having one dimension significantly larger as compared to the other two dimensions will not give you a plane strain condition. You have to take into consideration the boundary condition and the loading scenario. So this thing should be very clear to you, as I also mentioned in the previous lecture, that only satisfying the geometry is not enough. You have to satisfy the boundary and the loading as well. In any case, so now you have some idea about what plane strain is. So let us proceed to the mathematical part, where we will talk about first we'll talk about the stress strain relation in plane strain condition, and then we'll talk about compatibility equation and try to figure out governing equation for plane strain. Okay, so let us start. So, okay, so we are talking about plane strain, right? And we are interested in the stress strain relation. So for 3D, we have the following relation, which is epsilon xx, epsilon yy, epsilon zz, and this is in 3D we're talking about gamma xy, gamma xz, gamma yz, and this is the general case in 3D. And this is equal to, so you have 1 by E minus nu by E minus nu by E minus nu by E 1 by E minus nu by E minus nu by E minus nu by E 1 by E, and then you have everything else to be 0 on these 3 row columns, and then on the diagonals you have 1 by G, 1 by G, and 1 by G. Right? And then if you write it like this, this is your compliance matrix, right? And obviously you have your stresses here, the 6 stress components, which are sigma xx, sigma yy, sigma zz, tau xy, tau xz, and tau yz. Now remember that we are talking about the plane strain condition. And what happens in plane strain condition? Okay, let me change the color. So in plane strain condition, this is equal to 0. This is equal to 0, and this is equal to 0. So let us start from the shear components. So what do we have from the equation? Let us see. Gamma yz is equal to tau yz by g, which implies that tau yz is equal to g times gamma yz, which is equal to 0. Why? Because gamma yz is equal to 0. So tau yz we can find it to be 0. If we use the same thing on this gamma xz, we will see that tau xz is also coming to be 0, and this is because gamma xz is equal to 0. So now there is one more term which is the normal component. The shear components is straightforward. If stress is 0, strain is 0. If strain is 0, stress is 0, and that's it. So now let us come to this epsilon zz equal to 0. So let us see what we have. Epsilon zz, which you should remember is equal to 0, is equal to sigma zz by E minus nu by E sigma xx plus sigma yy. And remember that this whole term is equal to 0, which implies that sigma zz is equal to nu sigma xx plus sigma yy. So this is your relation. So between sigma zz, sigma xx, and sigma yy. Relation between sigma zz, sigma xx, and sigma yy. So this is the relation between the three components. Now, so which means there are only two independent stress components, because if you know sigma xx and sigma yy, sigma zz can be represented in terms of the other two. So what do we have? Let me write it down. We just got that sigma zz is equal to nu sigma xx plus sigma yy. This implies that there are only two normal stress components. This implies that there are only two normal stress components. Okay, there is one. It should be two independent. The third one is there, but that is not independent. So there are only two independent normal stress components. So that is something we should remember. Now, what happens to sigma xx and sigma yy? Let us see. So we have epsilon xx is equal to sigma xx by E minus mu by E sigma yy minus mu by E sigma zz. Now if I call this equation 2 and this as equation 1, what I'm going to do is I'm going to substitute equation 1 into equation 2. So substituting equation 1 into 2. If you substitute equation 1 into equation 2, what are we getting? Let us check. So that will give us epsilon xx is equal to sigma xx by E minus mu by E sigma yy, and then there is minus mu by E, and then inside the bracket, instead of sigma zz, we write the right hand term, which is nu sigma xx plus nu sigma yy. So let us see what we get here. So if you see sigma xx by E, so all the terms are having E, so I can take 1 by E outside. And then if I take sigma xx as common, I get 1 minus nu. 1 minus nu square actually, right? And then let us come to the second term. And in the second term, what we have is minus nu by E sigma yy. That is what I'm taking as common. And then inside, I will have 1 plus nu. Right? Now, this 1 minus nu square, I can write it as 1 plus nu times 1 minus nu, and 1 plus nu can come outside. So that will give us 1 plus nu by E, and then we have 1 minus nu sigma xx minus, look into this term, so this will remain minus nu sigma yy. So this is the relation between epsilon xx and sigma xx and sigma yy. Similarly, if we have epsilon yy, that will look something similar, which is 1 by nu by E, and then you will have nu sigma yy minus sorry, 1 minus nu sigma yy minus nu sigma xx. So we have sigma epsilon xx in terms of sigma xx and sigma yy, and we also have epsilon yy in terms of sigma xx and sigma yy. Now, like what we did in the, you remember what we did in case of the plane stress condition? What we did in case of plane stress condition was represent sigma in terms of epsilon. And we are going to do that. But before that, let me write down the strain stress relation in matrix form. So first, let me clear some space. So erase whatever is above this point. So let me clear this part. And then what we will do is we will write the strain in terms of stress, but using the matrix relation. So basically, it will be a 3 by 3 tensor, or sorry, 3 by 3 matrix. So this is the case. So let us see now. So if I write epsilon, I have epsilon xx, epsilon yy, and gamma xy. And then you see 1 plus nu by e can come outside. So 1 plus nu by e, I'm keeping it outside. And then inside, what do I have? I have, let us see, what do I have? Okay. So first term is this one. So first I have 1 minus nu. The second term is minus nu. Then it is minus mu, 1 minus mu, 0, 0, 0, 0. And then there should be 1 by g. I mean, at this location, there should have been 1 by g, but we know that 1 by g is equal to 2 into 1 plus nu by e. And this 1 plus nu by e is already outside, so that remains only, that keeps only 2. So that makes this term two. And then we have sigma xx, sigma yy, and then what do I have? Let me see. We have tau xy. So this is the strain stress relation, strain stress relation for plane strain condition. So this is the stress strain relation for the plane strain condition. Remember that there is another equation which is hidden here, and that is sigma zz is equal to nu sigma xx plus sigma yy. So this equation is also there, but that is hidden. We are only considering the independent components. So now let me erase whatever is not needed, and then we will try to find out the stress in terms of the strains. So basically, we'll try to find out the stiffness matrix. So let us delete. So we only need the equation that you see on this, the matrix equation that you see. So that is the only thing we will retain, and everything else will be basically deleted. Everything else will be deleted. And then let us see what can be done. Right. So we will do something similar. as we did for the plane stress condition, which you already know from last lecture. Uh, Green, I don't like it anymore, so let me make it red. So let us see what is epsilon xx. Epsilon xx is so this part is common, so I'm not writing this part, okay? So, or maybe I'm writing it as a. So there is one a which is common, and then what do we have? 1 minus nu sigma xx minus nu sigma yy. That is epsilon xx. Epsilon yy, what about epsilon yy? That is a. Let me write it like minus nu. Then there is this sigma xx plus 1 minus nu sigma yy. So let me call this equation 1a, this as equation 1b, and we want to solve for sigma xx and sigma yy. So what can we do? We can multiply the first equation by nu, the second equation by 1 minus nu, and add it up. So multiply this by nu, multiply this by 1 minus nu, and then you can add it up. So what happens when I multiply this by nu and this? So on the left hand side, what do I have? Nu epsilon xx plus 1 minus nu epsilon yy. That is your left hand side. On the right hand side, we have a nu 1 minus nu sigma xx minus nu square a sigma yy. So that becomes the first term, and we are adding it. So then minus a nu 1 minus nu sigma xx plus 1 minus nu whole square a sigma yy. And these two will cancel out. And what do I have at the end is yy times, so a can come outside, so a sigma yy times 1 minus nu whole square minus nu square, so that is a square minus b square, and that is equal to nu epsilon xx plus 1 minus nu epsilon yy. And then this bracket we can write it as a sigma yy. Then in the bracket what do I have? 1. So first is a plus b. So 1 minus nu plus nu. So that is basically 1. And then we have 1 minus nu, which is 1 minus 2 nu. And this is equal to nu epsilon xx plus 1 minus nu epsilon yy. Last equation. So sigma yy is finally then coming out to be, what is a? I mean, we need to write it down. A is 1 plus nu by e. So 1 by a is e by 1 plus nu. And when you do this calculation, this becomes 1 minus 2 nu. Right? And then what do we have inside the bracket? is nu epsilon xx plus 1 minus nu epsilon yy. So this is the relation. So I wrote 1, so let me write it down as 2. Now I'm going to remove everything else except this final form. So let me erase it. So let me erase all this, as this is no longer required. So let me erase it, and then what I will do is from similarity, I will write down sigma xx in terms of epsilon, and then we'll try to write the stiffness matrix, that is the stress strain relation, where stress is represented in terms of strain. So I think this much space should be enough. If needed, I can delete later. So let us write down. So sigma yy we can see. So what is sigma xx? Sigma xx is again E divided by 1 plus nu 1 minus 2 nu, and then it will be 1 minus nu epsilon xx plus nu epsilon yy, right? And then we have tau xy, and tau xy will not change, so that is g times gamma xy, which is E by 2 into 1 plus nu times gamma xy. So we need to write it in matrix form. So I need some more space. Let me erase some more space. But that is the final thing for this slide. So let us see. All right. So let us see what do we have. So yes. So finally, the stress strain relation is written as, you have sigma on the left hand side now. So sigma xx, sigma yy, tau xy, and this is equal to E divided by 1 plus nu 1 minus 2 nu, and then let us see what we have. So we have 1 minus nu 0, nu 1 minus nu 0, 0, 0. So here let us see, E by 1 plus nu has come outside. This is the additional term, so this becomes 1 minus 2 nu by 2. And then what do we have is epsilon xx, epsilon yy, and gamma xy. So this is your stress strain relation when for the plane strain condition. So this is the stress strain relation for plane strain condition, right? So previously we wrote down the strain stress relation, where strain was represented in terms of stress, and now we have written the stress strain relation, where stresses are represented in terms of strain, and you can see that the stress strain relation for plane stress condition and the stress strain relation for plane strain condition are not same. They are different from each other, right? So we did. So this is what I have already shown you. So these things are already shown. And then what do I have is, okay. So, yeah. So anyways, so let us see. So the conclusion that we draw is stress strain relation for plane stress and plane strain uh, condition for plane stress and plane stress conditions are not similar, are not the same. So that is the conclusion we draw. And now what we are interested in is to write down the constitutive relation and then see if we can if we can arrive at a single equation, single partial differential equation which satisfies the compatibility condition as well as the equilibrium condition. Similar to what we did for the plane stress condition, we want to do the same thing for the plane strain condition. Okay, so for that, first what we need is the strain in terms of stress. So let us write that down, and then we will see where it takes us. Right. So epsilon xx is equal to 1 by 1 minus nu square sigma xx minus nu into 1 minus nu sigma yy. I have to check it once, whichever it is 1 minus nu or 1 plus nu, I need to check 1 plus nu, right? So that was wrong. So epsilon xx is equal to 1 by e, then there is 1 minus nu square sigma xx minus nu 1 plus nu sigma yy. And similarly, epsilon yy is equal to 1 by e. There is, so this will come first. So what we can do is, okay, let me write it like this: 1 minus nu square sigma yy minus nu 1 plus nu sigma xx. So let me call it equation 1a, this as equation 1b, and this is the same slide where everything will now be carried out. So first let us write down this strain compatibility condition. So similar to what you saw in case of plane stress, in plane strain also there is a single compatibility equation, which is del 2 epsilon xx del y2 plus del 2 epsilon yy del x2, and this is equal to del 2 gamma xy del x del y, and this I am calling equation 2. So what we are going to do is we're going to take this 1a and 1b and substitute it into equation 2. I mean, same thing we did previously. So substituting 1a and 1b into 2. we have, so what do we have with that? Let us see. So del y, del 2 del y2 is outside, and then instead of epsilon xx, I can write this term, which is 1 minus nu square sigma xx minus nu 1 plus nu sigma yy. And I'm not writing 1 by e, or I can write it here actually. So let me write it down here. I mean, ultimately, this 1 by e will cancel out. I mean, you have already seen it. You have already seen this in case of plane stress, and the same thing will happen in plane strain. So, anyways, coming to the second term. Second term is del x2, and then we have epsilon yy, and epsilon yy is so epsilon yy is 1 minus nu square sigma yy, and then minus nu 1 plus nu sigma xx. And then when we come to the right hand side, what do we have? We have gamma xy. So gamma xy, you can write it as g, I mean tau xy by g. So 1 by e will come there. So g, 1 by g is outside, which is 2 into 1 plus nu by e. E cancels out as was promised. And then what do we have is del 2 tau xy del x del y. Okay, right? Can we simplify it further? Yes, we can. So let us simplify it further to see what we have. So if we simplify it further, we have 1 minus nu square del 2 sigma xx del y2 plus del 2 sigma yy del x2. So basically what I've done here is I've coupled this term with this term. And then let us couple the other term. So for that we have minus nu 1 plus nu. And if we do that, we have del 2 sigma yy del y2 plus del 2 sigma xx del x2, right? So we have now coupled both the parts, and what happens on the right hand side is nothing. 2 1 plus nu del 2 tau xy del x del y. And this is the solution for now. Now I'm going to keep only this expression, the final expression, and delete everything else. Let me think whether I will need 1a and 1b again. I don't think I will need 1a and 1b, so I can remove that as well. But let me start removing it from the bottom. So we have the final expression here, and we'll come back to the final expression in a while. But for then, let us do one thing, and that is let us derive whatever is remaining. So let us see. Okay. So I'm keeping the top one, although I don't think I will need it, but I don't want to write it again. And maybe I can make mistake while writing it again. So let me keep it. All right. So now you remember what we did in the previous lecture? The same thing we are going to do. Let me change the color. So in the previous lecture, we took the stress equilibrium equation, differentiated them to arrive at a solution, and then replaced it into the compatibility equation. And that's what we will do here. So let us write down the stress equilibrium equation. And this part is exactly same as the plane stress condition. So I will go through it very quickly. I will just write it down. So this is del sigma xx del x, del tau xy del y plus bx is equal to 0, which implies del 2 sigma xx del x2 plus, so del 2 tau xy del x del y plus del bx del x equal to 0. So this is the first equilibrium. The second one is del tau xy del x plus del sigma yy del y plus by is equal to 0, which implies I'm going to take derivative of this with respect to y. So the first term will be this one. So I write 2 here. The second term will be del 2 sigma yy del y2. And then the third term will be another additional term, which is del by del y is equal to 0. So I'm now going to erase the. I'm now going to erase the this equilibrium equation, because what I need have been derived already. And then we will work with, what is remaining actually. So let us see what is remaining. So with this equation, 2 del 2 tau xy del x del y, this is what I need, and this is equal to minus del 2 sigma xx del x2 plus del 2 sigma yy del y2 minus del bx del x plus del by del y. Right? So this is the equation that I will need. So let me box it. This portion I don't need. And now this equation, let me call it equation 3, this as equation 2. So what I'm going to do is I'm going to substitute equation 3 into equation 2. And let us see what we arrive at. So substituting 3 into 2. So first comes 1 minus nu square. This I'm going to call as b. So it is 1 minus nu square b minus nu 1 plus nu. This is equal to a is equal to, so we have this 1 plus nu, which will stay as it is. Because of this minus signs here, one minus will come. This is a so the first term is a And then what do we have? Let us see. We have one A here. And then we have plus del Bx del x plus del By del y. Now this 1 minus nu, let me write it as 1 plus nu into 1 minus nu. So this was 1 minus nu square, right? So I'm going to write it as 1 plus nu into 1 minus nu. And if we do that, this 1 plus nu, this 1 plus nu, and this 1 plus nu will cancel out. And what do we have? Let us see. So we have 1 minus nu times b. This a will come to the other side. So that will become plus, so this is 1 minus nu. So 1 minus nu times a, and that is equal to minus del bx del x plus del by del y. So all that is remaining for now is to bring all these things together and then write b and a in their original form. So this is the only equation that I need at this point. Everything that has been written before this and everything that has been written after this can be removed. And I'm going to do that. I'm going to remove. So let us see. So first I'll remove what has been written after this. And then if needed later on, I'll remove what has been written before this. But for now, let us keep it like this. So what is B? B is del 2 sigma x del y2 plus, del y2 plus del 2 sigma yy del x2 plus del 2 sigma xx del x2, this is A, remember, plus del 2 sigma yy del y2. So the first two terms are B, the second two terms are A, and then is equal to minus 1 by, this 1 minus nu will come into picture now. And then in the bracket, you have del bx by del x plus del by by del y. So now we are in a position where we can write the final expression, and the final expression is del 2 del x2 plus del 2 del y2 sigma xx plus sigma yy. This is equal to minus 1 minus nu del bx del x plus del by del y. And this equation clearly is different from the equation that we got in case of the plane stress condition. So this is the governing equation for plane strain condition, right? So this is the governing equation for the plane strain condition. As a special case again, if Bx and By are uniform or zero, if Bx and By are uniform or 0, in that case, this equation reduces to the same equation that we got in case of the plane stress condition. And this is equal to 0. This is same as the plane stress condition. So what we did was we started with the compatibility equation. We represented the compatibility equation in terms of the stresses, and then we took the stress equilibrium and brought it into picture, coupled those, and arrived at the governing differential equation, which is this one. So basically, this is one single equation which satisfies the compatibility condition and all those things. And then we considered the special case, which is in most cases you will come across, and that is the body force is uniform or 0. And if the body force is uniform or 0, in that case, what is happening is, as you can see, the plane strain equation and the plane stress equation becomes same. Now, does that mean that you will have the same result? No, because although the equations are same, you will in most of the cases have a different boundary condition. So the equation is the same. The boundary condition in most cases will be different, and as a result, your results will be different. However, the governing equation is same if the body force is uniform or 0. So let us see what we did. So all these derivations we have done, and this is the final result that we got. And then this was the conclusion that we draw just now. So in case body force is uniform or 0, the final equation for plane stress and plane strain conditions are the same. So I will stop here. So this is it for plane strain. Okay, this is wrong. This should be plane strain actually. So this should be strain. Let me check what is there. So this is correct. This is only wrong. Okay. So I will stop here, and then in the next lecture, we will talk about something known as Airy's stress function. So you can see we have the governing differential equation in terms of stress. So related to that, in some sense, we have what is known as the Airy's stress function, and we'll talk about it in our next lecture. And we will also see, solve some problem, one problem using the Airy's stress function. So thank you, and we will meet again in the next lecture.